In this video, we're going to talk about ways to protect a host-based or a host system. So this would be protecting a server, a workstation, a computer, whatever, but some kind of device. So we're not talking about protecting specific applications or data. We're talking about the overall system itself, some of the techniques we can use. And most of that revolves around the operating system, right? Because the operating system, for all intents and purposes, is basically the system. Most systems have, and most modern computing platforms have an operating system. Even embedded systems, even a thermostat has an operating system if it's a computer, typically something like a very lightweight version of Linux, for example. So when you look at how operating systems work, you typically start with the hardware in the middle, and you abstract that hardware from application systems by having an operating system wrap around that. In most cases, that operating system, that core portion of the operating system that works directly with the hardware. And when I say the hardware, I'm talking about memory, the microprocessor, and things like that. We abstract all that stuff through a kernel. So the kernel is the special software that interacts directly with the hardware. And then surrounding the kernel, you might have the shell. So I'm sure some of you have heard of the shell. I ask you to create access to a shell for many of my classes to work with some of the tools that are available in the Unix shell, for example, in various academic Unix environments. But so the shell is typically how we interact with the kernel. So you and I can interact with the kernel through the shell. So for all intents and purposes, the kernel is the operating system. Operating systems like Windows and Linux and so forth, they come with all these different components, but technically the operating system itself is the kernel. That is technically the operating system. A lot of the other stuff exists in the shell. So for example, the command line that we get with an operating system, that's really in the shell. The Windows environment in, say, Microsoft, a lot of the different applications that we're working with, they're all in that shell, and even the applications that come with the operating system. Even things like in Windows, you get Minesweeper, the game. That's comes with the operating system, but it's not a core component of the operating system. It's not it's not the kernel. A lot of times, a lot of the libraries that we work with, like TCP/IP, again, it's not part of the operating system. It's not part of the kernel. Although a lot of times it's very intertwined with the kernel. But things like the sockets library, they exist in that shell layer around the operating system. So, one last one that I do want to talk about for a second is things like Java and .NET. They're kind of a special case. So usually when you write code in, say, C++ or C or any of those low-level programming languages, although C and C++ are probably, two of, the very common ones, but there are other ones out there. But when you compile that code into bytecode, it runs in the shell, right? So it sits in the shell and it goes through the kernel to get to hardware. So it's not directly using the processor memory. Usually either has to ask permission from the kernel or is assigned those resources from the kernel. Java and .NET work a little bit different. There's sort of a program that runs in the shell that is the Java or .NET framework or virtual machine. And that's not like virtual machines like we'll talk about later, with virtualization at the hardware level and the operating system level. There's virtualization that sort of happens at the shell level. And that's what Java and .NET use. So there's really kind of one more layer outside of the shell, which is Java and .NET applications. And the reason I talk about this in a class like this is many business applications run Java and .NET. So a lot of organizations, Java and .NET is an extremely important part of the infrastructure. It's an important part of that data infrastructure. So we have to make sure we understand that and that we can protect that as well. So again, that's that one more layer that kind of goes around that shell. And the reason it's important to understand that is it's important to know that Java and .NET have that extra layer of abstraction that you don't have with other programs that were compiled in other languages. What that means pragmatically is that if you have a program that's written in .NET or Java, it doesn't stand alone. It has to run on a machine that has that virtualization, either the .NET framework or the Java VM. So you have to have those programs installed as well in order for them to work. All right, so now that we have that basic understanding of the operating system architecture, let's talk about doing some operating system hardening. So most operating systems include a bunch of components. They come with all these extras, and a lot of it are things that you might need, but not things that you definitely need. So one of the first things we can do when we're hardening a system or hardening at the system level is we can look at the operating system and look at all the different things that came with it, and we can remove any components that we do not need, the ones that we know that we're not going to need. So we can remove those because it's one less avenue of attack. It's one less attack vector. For example, Minesweeper comes with almost every version of Windows. It's a stupid little game. I'm sure a lot of you have played it. But do we need that game? Probably not. So that's something that we could maybe disable or remove access to. There are lots of little components like that. And you might be asking yourself, gee, Brian, what's the harm that could come of having Minesweeper on a computer? Well, if there's some vulnerability in Minesweeper that an attacker finds that can allow them to do something, with a system, then it's one more vector of attack. Well, if we don't even have that component, then it's one less thing the attacker can use against us. So we can make sure that we remove any of those components, which is then going to reduce the attack surface for the operating system. There's primarily two operating systems we see mostly in organizations. There's the third, of course, which is Apple, but the two major is going to be Windows and Linux. In Windows, we want to make sure we remove unneeded services and applications. So the vernacular in Windows is services, and remove any unnecessary network protocols and networking components. In the Linux world, we call them daemons. So, on a Linux machine, you're going to remove any unused daemons, any daemons that are not going to be used in that environment, as part of our baseline. And also with Linux, unlike Windows, we can completely remove the GUI, and it usually will have very little, if any, impact on the server itself. Windows, not so much. So Windows does have versions that can run without the GUI, but unfortunately, there's a lot of things that do not work in Windows Server without having the GUI. So there is a version of Windows Server called Core. The Core edition only has the command line, so there's no, in PowerShell, really it's the PowerShell, but there's no GUI component, there's no Windows, there's no start menu, there's no icons and things like that. It's really more like Linux where you just have a command line. But I think you can't run the .NET framework on servers like that. You can't run SQL Server. So there's a couple different applications that you won't be able to run. And I think .NET's the big one because, as I said, many organizations use .NET. But you can use that for things like domain controllers and so forth. So if you can use Core Edition, it's probably a good idea to use it for a variety of reasons. But one of those is that it reduces the attack surface of the operating system. I'm sure that all of you run some kind of an anti-malware on your computers, so networking presents a nearly unlimited attack vector for servers. The average Windows PC connected to the internet will be infected with malware in less than 60 minutes, and that's probably being very conservative, 60 minutes. I think it's probably closer to 60 seconds these days. But there are tools and products that are designed to stop those threats, and certainly it's recommended to run those on any Windows system. A little bit harder to find on Linux-based systems and some of the other platforms like Android and Apple and so forth. But if it's available, it's a good idea to run some kind of anti-malware. And sometimes they even come with the operating systems. I know Linux now comes with, many of the distros come with some tools for anti-malware. And of course, Windows has its own built-in anti-malware that's available for server, as well as workstations. So antivirus is the first type of anti-malware. There's a couple different ways to identify a virus, or really worms, viruses, all the different types of malware that we discussed previously in the course. There's a bunch of different ways to identify. Well, it's really two primary ways, I should say. I'm sorry. There's signature-based scanning and heuristic scanning. Basically, what these mean. So signature-based scanning is when we're looking for the exact signature of that virus or the fingerprint of that virus. So that could be something like a hash on that virus. Basically, what does the virus file itself look like? That's signature-based scanning. It's looking for attributes about the file. Typically, it's some kind of hashing mechanism. But that's the first way. So we're literally identifying the file, not necessarily by the name of the file, right? Because the name of the file could be anything. But we're looking at something like a hash, and we'll talk more about hashing in the encryption portion. So you can watch some cryptography or encryption videos to learn more about how that works. But basically, the concept to take away here is it's like a fingerprint. So it's identifying through something inherent about that malware, that virus. Heuristic scanning is looking at behavior. So heuristic scanning is looking at what programs are doing to try to identify them as a virus based on their behavior. So if you think about policing, one technique for policing is I try to identify people. So if we know who they are, we know whether they're wanted criminals and so forth, and we can make some assumptions based on that. But we could also look at how people are behaving to try to define whether or not they're a criminal. So we can look at both of those things, and typically they do both, right? Typically, most police departments will both try to use identification along with observation to try to identify criminals. So, again, we have those two techniques. Once we identify malware, the next step is to neutralize or remove, which is something that most antiviruses will do for us automatically, which is one of the advantages to having an antivirus do that. We could certainly identify a virus on our own, but by the time we do, we're pretty slow, most humans, at doing that, so it probably already did a lot of damage in that case. Some of the features you'll have in most antivirus, you'll have things like automatic updates for that signature-based and heuristic-based scanning. So they'll automatically update it with either new techniques for the heuristic scanning, new behaviors that they're looking for. And of course, the more important one is the signature-based scanning. As new viruses are identified, those signatures are added to a signature database in the antivirus. Typically, they do automated scanning. So they're automatically scanning in the background. They automatically scan media when you plug it in. So you plug in a USB drive, put in the CD-ROM, and so forth. It's going to automatically scan that stuff. In many cases, it'll automatically scan files that are being downloaded from the internet. And then the user could always manually scan their files. In addition, they can also scan emails or attachments that come in, I should say, with email. And they usually have some baked-in method to resolve any threats that it does find. Sometimes they quarantine those files. Sometimes they just automatically remove them. So there's some different techniques there as well. But almost all antivirus, works in the way that I described here. Anti-spam is basically trying to block spam from within the organization. I should mention here that I think anti-spam is quickly becoming not our problem for most organizations, because I think a lot of organizations are now starting to use the cloud for email. They're kind of moving that responsibility to a third-party provider like Google or Microsoft or whoever. So in those cases, it's becoming less important for us to scan emails because it's happening through a third party. But if you do have to do something to detect spam, one way to do that is blacklisting. So you can blacklist known spam senders. You can use content and keyword to look for things that might indicate that it's spam. Look for only trusted servers. Delay-based filtering is basically a technique where you're taking advantage of the fact that the spammers have to send a massive amount of email very quickly. So you can basically delay. So when they call your SMTP server to tell you that it has a message to deliver, you can delay the response. That way they'll drop the connection because they don't have time to wait. So that's one way you could do it. And usually legitimate email traffic won't be affected by that delay. PTR and reverse DNS. I don't know in this course that we talk too much about DNS, but a PTR record or a pointer record tells you the IP address for a host name, and likewise, that's DNS rather, and a pointer record gives you the DNS name for an IP address. So if mail comes into an SMTP server for relay, you can look at the IP address from which that message came, and you can do a pointer record search, which will tell you the accompanying host name for that IP address. So if it comes back for a completely different organization, so if the from address in the email says it's from drexel.edu, but the pointer record says it's from hacker.hacku.hack something, then it's probably not legitimate. You can throw away that message, for example. Callback verification is if you get an email message comes into your SMTP server could then try to initiate a connection back to that URI to the FQDN. So if it gets mail from drexel.edu, if the from address is drexel.edu, it can try to open an SMTP connection to drexel.edu to make sure that that's a valid email sender. Obviously, if it's a spammer, they're not going to accept SMTP messages. So it'll be less likely that they're going to accept it, and then you know that you can discard the message if they don't. You can use statistical content filtering, where users basically are telling you over time what looks like spam, and then you can use that to sort of build a database of what typical spam looks like. It's sort of self-learning almost. I'm sure a lot of you have used things like Gmail or Hotmail, where you can report spam, and then they can use that over time for statistical content filtering. And then you could use basic rules. If it contains the word Viagra, for example, and you don't work for a urologist, then there's a good chance that it's spam. Egress filtering. So egress basically means exit filtering. So we can check emails that are leaving our network, through an SMTP relay, and make sure that it's not spam, to make sure that we're not relaying spam, which is something that some malware tries to do. And then a hybrid filtering is where we're combining these different filtering techniques. So we're using delay-based filtering, callback verification, statistical content. We're kind of combining all of these different techniques to do filtering, which is very effective, right? When you have these multiple layers of protection, it's much more effective than just choosing one of these, of course. Anti-spyware basically can monitor memory and network to detect spyware. That's, they're pretty straightforward. Pop-up blockers, I'm sure a lot of you have been annoyed by pop-up blockers, but they basically prevent websites from opening new windows or tabs without the user's consent. So if something's trying to be opened without the user saying it can open it, most of modern browsers will automatically block those pop-ups. There was a time, years ago, where you'd have to download a third-party utility to do this, but just about all the browsers today have a pop-up blocker baked in, so we don't have to worry so much about that. Patch management we've talked about in other sections of the course. Obviously there's application patch management, but we can do that at the operating system level as well. Oops, sorry, I hit the wrong button here. There's hot fixes, which addresses immediate needs, usually very focused on a specific issue. Then you have patches, which fix known bugs and might contain enhancements. They're a little bit more formal than a hotfix. So a hotfix is sort of a quick release for a zero-day vulnerability. A patch might contain many different hotfixes, or it might contain some additional features, or fixing a kind of a batch of bugs that have been fixed in the software over time. But they're generally a bit larger than a hotfix. And then a service pack is a collection of a whole bunch of hot fixes and patches all in one big service pack. And this vernacular is mostly from Microsoft. So I think Microsoft kind of coined a lot of this vernacular, and a lot of vendors kind of followed suit with using the same vernacular. So most vendors tend to use the same conventions when they're talking about patch management. So patches and updates in most operating systems can be automated. So you can turn on automatic updates and things like that. But it is important to note that many organizations, we don't do those automated updates because of availability, right? If you remember IT security, we talk about the triad: confidentiality, integrity, and availability. And if we do a patch that's going to break functionality, even though we want patches, and that's an important part of the confidentiality, integrity, it may break the availability portion if it's breaking functionality that we need. So in many cases, we'll have some type of framework in place that's going to make sure that patches aren't going to break any functionality that's required or break any applications and things like that. So there might be some testing we do first, and then we release patches internally. So again, it's all about making sure we control how those patches and updates are applied throughout the network. Another technique is whitelisting and blacklisting. Basically, blacklisting is denying the execution of any program that we know to be bad. So it can be difficult to manage dynamic threats because as a new threat emerges, we have to add it to the blacklist. But it does require the least amount of management. We don't have to do as much for blacklisting because we only have to touch the blacklist when we find new applications that are a threat, and we add it to the blacklist. But as I said, it's while it's the least amount of management, it's also the least secure because new threats are not going to be blacklisted automatically. So the alternative is whitelisting. Whitelisting is basically providing a list of only the programs that are allowed to be executed. The problem with whitelisting is it requires management for the acceptable application list. In other words, somebody has to manage that list of applications that are allowed. And every time somebody needs to access a new application, they have to put in a request and somebody has to act on that request. And this could affect the availability. Again, in the CIA, we have the availability. This could affect the availability. So it's very effective for new threats, because if there's some new program that has some vulnerability, it's not going to run on our network because we disable everything by default anyway. And we have to vet every program that we're going to whitelist. So, it's more likely that it's going to get blocked. So in Microsoft Windows, we do this with software restrictive policies. We can do it at the machine level. You can use UAC or App Locker, which is at the user level. And there's ways to do this as well with the other operating systems like Linux, Unix, and Apple. A trusted operating system is basically an operating system designed for security. They're typically required for government and military. It's in the common criteria for IT security. So there are versions of trusted, it's codified rather in the common criteria for IT security, what constitutes a trusted operating system. But there are versions of both Linux and Windows that have the features required to be considered a trusted operating system. It's basically a more secure alternative to the standard builds of those operating systems. So whether it's Linux or Windows, you can start with installing a plain vanilla Windows or Linux, and then you can do some modifications, you can do some hardening and so forth to bring it into compliance as a trusted operating system. So Windows has a roadmap to do that with most of the newer versions of Windows Server from 2008 and up. And Linux, most of the newer distros of Linux include the components that you would need to make it a trusted operating system. For the most part, that's facilitated through a package called SC Linux. So firewalls, we can, we talk about firewalls in the network security portion or network security videos, but firewalls can also be local on the host. And really, kind of all firewalls run on a host machine, but each host machine could have its own firewall that's doing additional firewalling. Starting with Windows XP, Windows included a firewall, as I think they thought it was a good idea after 30 years of Linux including a firewall. 30 years is a little bit of an exaggeration, but the beginning of time basically. But Linux has been using a package called IP tables, which is a core component of the kernel. And there's a newer one now than IP tables, which I can't recall the name of exactly, but it works very similar. It also included TCP wrappers, which is even more secure. Although it does affect performance using TCP wrappers, but the combination of IP tables and TCP wrappers is basically what firewalls do. In fact, if you have a firewall, maybe a piece of a hardware-based firewall, typically they actually are using IP tables under the hood. So IP tables is a pretty core component of most firewalls. But we can configure IP tables in the Linux world. We can configure the Windows firewall in the Windows world to do additional firewalling, so we can block traffic from leaving the host, and we can block traffic from entering the host unless it's in our rules in the firewall to allow that traffic either in or out, which is important to do it both ways. In addition to firewalls, there's also host-based intrusion detection systems. We'll talk about intrusion detection systems in networking slide decks as well. But there's network-based intrusion detection systems, but you can also have a host-based intrusion detection system or a HIDS. And that's kind of what a HIDS looks like. It's very similar to an antivirus. In fact, many antivirus programs are also host-based intrusion detection systems. They're not only searching for viruses and malware, but they're also looking for signs of an intrusion, of some kind of vulnerability in the system or something, in some scenario where it appears that an attacker has control of the computer. They can look in log files. They can look at the traffic coming in and out of the system. They can look in audit trails. For example, in Windows or Linux, there's audit logs. And it can identify the malicious activity by looking at activity that might be happening at strange times when no one's supposed to be using that particular service or that computer. They can look for authentication failures, so repeated attempts to access the system. A plain vanilla antivirus typically won't notice that, but a host-based intrusion detection system is watching for those authentication failures. It's monitoring the logs in Windows or in Linux, looking at those authentication failures to look for something that's outside the normal patterns. They might look for new user accounts that are getting created. people trying to access critical files. If you're in a Linux system and you try to access a critical file or a file you don't have access to, it'll typically tell you tried to access something you're not allowed. This has been logged. And somebody might look at that log. Well, that somebody's going to be the host-based intrusion detection system. And it's, hopefully it's not going to raise false alarms from just normal user behavior, just normal people accidentally trying to access files that don't belong to them, but instead look for systematic patterns that would be indicative of some kind of an attack. Modification or removal of binaries for the operating system or for core components and programs. Activity process or process activity, so looking at what different daemons or services are doing and looking for anything that's out of the norm, and any privilege escalation that's happening, giving somebody additional privileges that maybe is not expected. So all of this stuff can be combined by a host-based intrusion detection system to try to look for patterns of behavior that are indicative of some kind of an attack. And again, you can almost think of this as like heuristic scanning in an antivirus. It's kind of the same thing, but we'll talk more about intrusion detection systems in the network-based portion of intrusion detection systems. I'll talk a little bit more specifically about how they work and how they're configured. But for right now, it's good to understand that there is a host-based version of intrusion detection systems. And we talk about layering in IT security. That's one of the concepts of IT security is layering. So we talked about that with firewalls. So we could have a network-based firewall, but each individual host and server could also have a firewall protecting itself. So that's 2 layers. And likewise with intrusion detection system, we can have a network-based component and also the host-based component. So some of the advantages of a host base is that they understand the host environment, and they have a lot more information about that host than a network-based system would. They have much more context than the network-based system would about that specific host. So it can reduce false positives. The data on the host may be examined unencrypted. So when the data is on the network, it's typically hopefully encrypted. But when it's sitting on the server itself, the host-based system may have access to that data unencrypted. So it can make more intelligent decisions as to what's going on. And it can also be application specific. But some of the disadvantages of a HIDS-based system or a host-based intrusion detection system is that it has to be on every single system in order for it to be effective. It has a higher total cost of ownership because we have to run it on every system and install it and maintain it. It uses additional system resources. It does not relate to the activities outside the host. In other words, it has no context of what's happening on the rest of the network. So it may miss an intrusion because it doesn't understand that someone's also trying to do the same thing on 5 other systems. And maybe that traffic doesn't, it looks relatively benign on just a single host, but when you aggregate that with what's happening across many different systems, then it would appear to be more nefarious. And they can also be compromised or disabled. So, certainly some good things about HIDS, but there's a few things to be aware of that are a disadvantage. And again, this goes back to that layering concept where it's a good idea to have these different layers of security. So most of them have an integrated firewall. They can have behavioral as well as signature-based. Behavioral is just another term for heuristic. So when I talked about heuristic with antivirus, it's the exact same concept. They have application control. They can be, a lot of times they have enterprise management. In other words, from some console, you can manage it across the enterprise. They'll typically have malware detection. So you can really use a HIDS as sort of a catch-all for a lot of these little host-based security components that you might need, like anti-malware, antivirus, and a intrusion detection system on the host. So as far as hardware security, we've got servers, workstations, devices. To protect all that stuff, one way is through cable locks. We can put things in safes or locking cabinets. I think in other courses we talk much more about physical security, so I don't want to get into that in too much detail in this slide deck. So baselining, we've talked about baselining in other slide decks. We talk about baselining, and in the operating system world, we can do operating system baselining, which is the same technique that we might have used for application software. Basically, we create a uniform baseline for widely implemented software and operating systems to use as a baseline for deployment. So if we've already identified what the absolute minimum components are, and we've identified what programs and what daemons and services and so forth that we need, and what additional components we need to secure a system, that becomes our baseline, and we can use that baseline for deployment and make sure that we're deploying a consistent image. And speaking of deployments, one thing that's made managing data centers and IT security much easier is virtualization. Certainly, virtualization brings some new challenges, but it also can make things significantly easier in some respects. So many systems can be running virtually within a single system. And the software that allows that to happen is called a hypervisor. Some common hypervisors are things like Microsoft Hyper-V, VMware, which is probably the most popular, Citrix Zen, Parallels, which runs on a Mac, and then Oracle VirtualBox, which is a kind of a free alternative to a lot of these, and even things like OpenStack. There's other virtualization platforms out there. But one thing that's pretty cool about virtualization, it allows you to do snapshots. So once you baseline a system, you can take a snapshot and you can use that to build other systems and very quickly deploy other systems. So it has certainly made deployments a lot easier and much more secure, because we don't have to worry so much about people straying from that standard that we come up with in IT security. An important concept with virtualization is this idea of elasticity, where where resources can be dynamically assigned to virtual machines. It's very difficult to do that in physical environments, but in a virtual environment, because everything's kind of swimming in the same hardware pool, you can dynamically allocate resources from that pool to different servers. So if one server doesn't need a lot of memory, but another one does, you can kind of shift down the memory on one system and shift it up on another system. Some virtualization platforms allow you to do that dynamically without even restarting machines and things like that. Things like VMware's products, for example, some of the enterprise products allow you to do things like that. And finally, sandboxing, which is important in IT security, because with sandboxing, we can isolate systems in a virtual environment to do testing, to do vulnerability scanning and things like that, maybe to try different things. We can even take a virus that we found and infect it to see how it works on a system running in a virtual environment that's isolated from the network through that hypervisor. So certainly some new tools that we have access to. And, this is one of those topics that you could take a whole course on virtualization and virtualization security. It's a whole topic sort of unto itself. So in this slide deck, I talked about securing the operating system. So I talked about all the different things we have to worry about with the entire host, not just single applications or data, and some of the things that we can do to secure the operating system.